Now, if you correlate such a flow potential per time point with the in-strength gradients, this is what you get. Here you see the average of these correlations across all 100 simulations for the left and the right hemisphere. And as you can see, this pretty quickly after the randomly initialized phases have started to produce traveling waves, settles at a strong correlation of about -0.7. So indeed, it seems that traveling waves emerge in such a model, and they do follow in-strength gradients. Now, to really see if the in-strength gradient is what determines the propagation direction, I built a control model where I shuffled these connection strengths within the existing topology, everything else being equal. And you can see it looks quite incoherent first, then starts to synchronize. Applying the detection method to this model showed that only 2% of all time points across all simulations produce traveling waves. In another control model, I tried to preserve the distance connection strength relationship while destroying the in-strength gradient. So here I basically fit an exponential model to the empirically derived distance connection strength relationship of the human connectome project subjects. And I used this exponential model to synthesize a surrogate structural connectivity. And this is what this model looks like. So here you see waves emerge, very strong ones. You see a clear rotating wave here. Yeah, so this is definitely strong wave activity, and as a matter of fact, the detection method identified waves in 98% of all time points across all simulations. This becomes very clear in the wave flow potential. So you see waves flow from frontal to parietal or posterior areas. So, and while this does not reflect the empirically derived in-strength gradients, this of course does follow the in-strength gradient distribution that was created by applying this exponential model to the specific three-dimensional embedding of these brain regions, which you see in the bottom here. Now, in another control model, I wanted to see if conduction delays are actually a necessary condition for waves to follow these gradients, in-strength gradients. So here everything is equal to the original model, just the conduction delays are removed. And as you can see, the activity seems quite incoherent at first, but now you can already see that there are smaller waves emerging. And in fact, the detection method found about 50% of all time points across 100 simulations produces traveling waves, so still a large amount of waves. However, once you correlate the flow potentials to the in-strength, you see across all simulations, they're hovering around 0. So it seems that conduction delays are actually necessary for these waves to follow the in-strength gradients. And of course, you might complain now and be like, yeah, Dominik, this is a very simple model. What about a more realistic model? So of course, I was interested in that question too, and built a control model where I replaced the Kuramoto oscillators with the so-called Janssen-Ritt model, which is a quite realistic model that incorporates pyramidal cells, inhibitory and excitatory interneuron populations. The pyramidal cells excite the inhibitory and the excitatory populations, and the interneurons in turn send back inhibitory and excitatory feedback. And to communicate with other regions, the pyramidal neurons send out excitatory long-range fibers to other regions and get input in turn. And of course, we still have to take into account the weakly coupled oscillator mechanism. So what have we learned? We have learned that the entities need to be self-oscillating. So in this case, I next set the parameters of the Janssen-Ritt model to produce about 10 Hertz oscillations when they're isolated. Everything else being equal, I use the same structural connectivity as before, empirically derived. And here's an example simulation of this model. So as you can see, this model does produce very strong waves. And again, I like to think that they do follow the in-strength gradients. As a matter of fact, if I applied the detection method to this model, I found that 90% of all time points across all simulations did produce traveling waves. And if we have a look at the wave flow potential, we do see clearly, this is again the average across all time points and simulations, that again a similar pattern emerges. And in the correlation of in-strength and flow potential, we see that after a while this model settles at a correlation of -0.4. Now you might say this is quite low, but I can already tell you that if I changed one parameter, namely the conduction speed, still within the biologically plausible range, I could crank this up to -0.8. So very strong correlations. So in summary, even with a highly biologically realistic model employing the structural connectivity and the realistic neural masses, we still see waves emerge, and they do follow the in-strength gradients. Now, returning to the Kuramoto full brain network model, I wanted to understand how the parameters affect wave emergence. So I investigated intrinsic frequencies of 1, 10, 20, and 40 hertz, so corresponding to the main brain rhythms of delta, alpha, beta, and gamma. I also varied one free parameter of the Kuramoto model, namely the global coupling strength, and the conduction speed, which determines the time delays between the brain regions. And here I chose a range from 1 to 10 meters per second, which is the biologically plausible range for white matter fiber conduction. And as a metric, we have in the first row the proportion of waves. So these are all kinds of waves that can emerge throughout all time points and across simulations. And here per parameter combination, I use 10 simulations because otherwise it's computationally quite demanding. And the second row corresponds to proportion of guided waves. So these are the waves that actually do follow the in-strength potential or the in-strength gradient, sorry. And the last one is the in-strength potential correlation, just to see if something reverts here in the direction, something like that. Okay, so if we have a look at the delta range, left and right hemispheres, we see that throughout all parameter combinations, almost 100% of time points across all simulations show waves, and they do follow the in-strength gradient. Now in the alpha range, we see that at low coupling strength and low conduction speeds, region emerges with fewer waves, and they don't seem to follow the in-strength gradient. However, most of the combinations still result in almost 100% waves and do follow the in-strength gradient. In the beta frequency range, we see this region down here expanding of no waves. And of course, if there are no waves, they don't follow the gradient. However, if waves emerge, they do follow the gradient. And in the gamma range, again, we see the same pattern. So this region of no waves expands. Again, if waves emerge, they also do follow the gradient. So again, to sum up, we have shown in this full brain network model that the empirical structural connectivity allows the emergence of waves and gradients of in-strength in this empirical structural connectivity actually guides the waves from temporal parietal areas to frontal and occipital areas. Okay, so now you might wonder, is there actually any evidence of these traveling waves in humans? And this is a quite challenging experiment to do, because you have to have quite a whole coverage of the brain and electrophysiological measurements, which, as you've heard, is anyways challenging to detect waves in. Plus, you need to associate the activity somehow to the brain regions associated with the structural connectivity. This is quite challenging to do. Nevertheless, there is already some evidence out there that suggests our brain network model has actually some legitimacy. And here is, for example, one study by Halgren and colleagues where they investigated alpha traveling waves during resting state in people with epilepsy. So again, they had ECOG areas implanted, as you can see here for one patient. And they averaged the phase map here and projected it onto the ECOG area. And as you can see, waves in the alpha range propagated from parietal areas to posterior sites. The same was true for another patient here. They propagate again from temporal parietal areas to the occipital lobe. And they have found this pattern throughout all their subjects. If the ECOG area was actually implanted a little bit more anterior in the brain, they found the pattern flowing from, or waves flowing from parietal areas to frontal sites. So this is very much in alignment with what this full brain model suggests. And in another study by Zhang and colleagues, they investigated alpha and theta traveling waves during a memory task. Here is what they found. So you see these little arrows, which represent the propagation direction. And also in this study, they found that waves emerged from the parietal cortex and traveled to occipital and frontal areas. And not only did they find a qualitatively similar propagation to our model, but they also investigated the distribution, spatial distribution of the frequency of these brain regions, or that was measured on the ECOG electrodes. And as you can see, this they in fact found a frequency gradient from high frequencies in parietal and temporal areas to low frequencies in frontal and occipital areas. And quite remarkably, our full brain network model produces the same frequency pattern. If you recall, we initially set the intrinsic oscillation frequency of all of these oscillators to a homogeneous 10 Hertz. So, but it seems that the combination of coupling strength gradients along with time delays actually suppresses the effective frequency of these oscillators until they settle in this phase-locked state. And that produces lower frequencies in frontal areas and in occipital areas, while the frequency remains close to 10 Hertz in parietal, orbitofrontal, and temporal areas. So as you see, there is already some evidence that experimental evidence that this model could have some value in predicting traveling wave behavior. And to conclude, so cortical traveling waves seem to be ubiquitous throughout the brain. We have seen a couple of mechanisms that might underlie neural traveling waves, such as delayed excitations, pulse propagation, and phase locking in weakly coupled oscillators. And finally, we have seen that the structural connectivity gradients might actually direct traveling waves. And that's it. So I'm happy to receive thoughts, ideas, and questions